Hi everyone, in this video we're going to build a LangGraph RAG agent. So this is going to be the architecture of the agent. So we have a router node. This router node decides based on the user query where to forward it. For example, if the user query is just a greeting like a hi hello, then router can generate the reply to that greeting and end the conversation. If the user query is something which can be directly answered by the LLM with its own knowledge, then it directly forward that request to the answer node, and then answer node generates the reply and end the conversation. If the user query requires to do some knowledge base or vector database lookup, then it forward that request to the RAG node. RAG node fetches the chunks and then it checks whether it is sufficient to answer that particular query. So whether the chunks are sufficient to answer that query. If it is yes, then it forward those chunks to the answer node and it generate the answer. If retrieved chunks are not sufficient to answer the user query, then we do the web search, and then web search node returns that request to the answer node, and the based on all the chunks and the web search research, it will generate the answer. So let me show this thing in action. So here is the agent in the Colab notebook. So first I have created this agent into the Colab. In the next video we will integrate this agent inside, let's say, the FastAPI, and we can deploy it. So let me show you how it works. So let's say I'm just sending a hi message and I got a reply from the agent, and we could see what's happening under the hood. So this is the langsmith where we could see all our LLM calls. So when I ask for the let's say when I say hi, there is only one node involved, which is the router node, and this router node was able to route it to the end of the conversation, and it has given me the reply. And this is what that particular LLM calls looks like. So it has root as end, and then it is reply. Similarly, what we just saw here from router, it directly went to the end. Now let's say I ask something that LLM can answer without doing any lookup. Like for example, I ask what is AI. This is something LLM don't require any lookup, and it should be able to answer directly. Now we can go and see what has happened there. This time there are two nodes involved. There is a router involved, there is an answer node involved. As we discussed earlier, from router it decided to forward that request to the answer generation node, and the answer generation node eventually replies. So we can see what has happened here. So the router node you know uh, decided to route that request to the answer node, and it didn't it generated any reply for it. And when it goes to the the answer node, it generated the reply for it. Now let's go and ask something that might require a lookup. So I'm asking, let's say, so I'm asking something. Let's say I'm asking. I'm sure that LLM doesn't know, me. So let's see what happens. Okay, this time we got some answer, and I'm sure that is not in my knowledge base. I can go and check what has happened under the hood. This time we could see there are a couple of nodes in all. So when it goes to the router first, the router decided to do the RAG. So it forwarded request to the RAG node. And what happened at the RAG node? So we do got maybe, let's see, we got some documents from the RAG based on the query. What we got, there is no threshold at the moment. And then here in the RAG, we got the RAG judge or a prompt that decide whether this information is sufficient. It is saying sufficient is equal to false. So this is basically this LLM structured output what we are using. You could see here we are passing the schema. And since the retrieved chunks were not sufficient, we basically do the web search. And web search we are using, let's say here, tabeli search, and that brings some more information about me from the web. And then eventually this all these things retrieved chunks and the the web search details what we got given to the final answer generation node, and it generate the final answer what you just saw here. But what if it could find directly something there? So I have a hypothetical document. Let's say what is or let's say when was founded. So I got some documents related to this fictional company called Greengrow. It is saying 2010, and this is something coming from the documents. We could verify this information. Okay, so here we could see from Okay, is that the thing? Okay, when was okay? This is one interesting thing happened now. So basically, what happened? This particular conversation already had the history of my, the answers, and we have seen in the previous request that we also retrieved some chunks, and maybe that chunk already has that information. The earlier retrieved chunk from the RAG had some information about that green grow. Yeah, it is their green grow company founded. That's why this is so good that it is directly generated the the answer without going to the RAG, because the information was already there. Okay, but what if information was not there already? So we can go, let me stop this run, and maybe I start the new thread to show you that okay, this is a thread. Let's say I start the thread as element. So this is a different conversation, and now let me ask the same thing, this one, and it is saying there is no information available about green grow. What happened? There's no information available. Let's see what happened under the hood. Ideally it should have gone and check, but we'll see what happened. So it went to the router, and it decided to generate the ideally it should have passed that information to the RAG node. Let me try once again. You could use GPT 4.1 instead of mini if you see that sometimes it doesn't do a good job. Okay, maybe I should also change the session. Okay, this time it is able to answer directly. What happened? Because we did I use this thread ID earlier? See what's happening under the hood. Okay, it did use the RAG this time. It did use the RAG. We could see that this. So there is some we just saw that one time it directly forwarded to the answer node. The other time it decided to do the lookup. I'm sure we could play with just the prompt. I just put a simple prompt here. We could add more detail here so that it always prefer to go to the RAG. So this is how overall architecture we have built a similar architecture for many of our clients and deploying the production. Some of these architectures are more complex, but this is the basic usually people have. They want to have some router node so that they could route the request. Then they need to make sure that whatever we are getting from the RAG, whether it is sufficient to answer, or maybe check for other source. Now here I just use the web search, it could be something else. So this is coming from the practical experience what we build for our client at the Future Smart AI. We do have some of the case studies here that you guys can go and check. Okay, so this was a very long intro, but I do wanted to show what exactly we are building. That's why we discuss the architecture and the demo. So if you find that this is something useful to you, then you can continue watching the tutorial to just to give you the glimpse what I'm going to cover. As you saw in the this LangGraph RAG agent, we are using some kind of a tools. It is multi-node. It also has a memory. So I'm going to cover all of those things. So there will be some LangChain LLM basic. Basically, how do we invoke the LLM? How do we add tools to the LLM? How do we get the structured output? Because we saw, we need a structured output from the LLM to decide, which node to go the next. And then we will build a basic LangGraph chatbot, and then we'll add the memory. Then we will add tools, and eventually we will have the final version that we just saw. Okay, so if you're interested, you can continue. You will get all the code from this collab notebook, and as I mentioned at the start of the video, this might be the long video. That the first part of this one is basically this collab notebook. If you guys are interested, you can you let me in the comments whether I should take this collab notebook and create a proper fast API, including everything, having endpoints to manage the vector database, and then serve this RAG agent as an API endpoint. So if you are interested, let me know in the comments. Okay, so let's start with this basics. And again, if you don't want to go through these basics, then maybe I'm not sure whether I will have a timestamp to the video, but you can directly go to that particular location in the video if you are interested. So let me clear some of this output because I think I have already used this thing. Let me do the clear all the outputs. Maybe, yeah. So we need to start with a, let's say we need a LangChain. We require LangChain OpenAI because I'm going to use the OpenAI LLM. The LangChain community, for example, let's say I'm using Tavily search or the DuckDuckGo web search or something, you require some community packages. And the LangChain core is basically all the things, the messages, the prompts you see, they all come from the LangChain core. So once we install these packages, I'm setting my OpenAI key, and then I'm also enabling the Langsmith that we just saw. That's how we are getting all those traces here. So you need to go to the Langsmith. All of these things I have covered in my earlier video. That's why I don't want to focus on those. Now let's say, so I still want to cover this basic LangChain and LLM invocation, to just make sure that uh, that whatever I'm building with the LangGraph, you guys, if you're not familiar with the LLM, at least you will have that concept refresh. And as I told, I have covered all those things earlier. So there is one video that I had covered, called LangChain expression language. This is where this basic invocation and how to use LLM prompts and all these things I have covered. So let's import the so we are using the LangChain OpenAI library. Basically, this is dedicated library for the OpenAI, and we are importing the chat model. So this is how we initialize any LLM in the LangChain. So we take that and we can specify which model we want to use, and there are other parameters that we can specify. I'm using GPT 4.1 mini, and the good thing about the LangChain is that you can invoke any component of the LangChain. That is what it's interesting. You can check the LangChain expression language, so that I can take any component like LLM, prompt, retriever, or anything that is inside the LangChain, and I can call the invoke method and see how it works. So here I'm invoking this LLM. So when we invoke the LLM, if you look at, we know that the LLMs are basically take the messages and give the messages back, the chat. So if I look at what is the response, we got. So we got response as an AI message, and this AI message has a field called contain. That is where our response in a string format, or and that's what I printed here. So I hope you are familiar with this thing. This is how basic, you could invoke an LLM, and we could see the same thing inside the the LangGraph. This is what we just ask LLM. This is how a typical Langsmith trace look like, and you could see whatever, as I told you, the chat LLM take the list of messages and give back a message as an output. Here we are passing a string, but ultimately this string getting converted into the let's say human message, that is going to the LLM, and then LLM is giving a message of type called AI, and that's what we get this response. Very simple. In the Langsmith, we could see that this is the model that we have used, GPT 4.0 mini. Let's go back here, and now let's see, as I told, right, we could pass a list of messages as an input. Now here I'm taking a system message. Basically this is like a higher level prompt, and this is the human message, which is let's say our input. So they are coming from the LangChain core. Human message is system message. Now I'm passing this list of messages inside this and invoke, and it should behave the same way what we just saw. This time, instead of one message, we should be able to see the multiple messages as an input. Okay, so here is the LLM, and as I see, the input has now two messages. One is the system message, the other one is the human message, and this is what the output we got from the AI message. So this is how you pass input to the LLM and invoke it. Now next, this is very basic, we don't want to get into this. Now let's see how we can attach tools to the LLM, because we know that we need to increase the capability of the LLM, and it can be done by leveraging the tools available. So here I have tried to use two three tools. One of them is a simple like a calculator. One is this DuckDuckGo search, and then the demo that we just saw earlier, we are using the Tavily search. So here, let's say for this demo, I'm using the DuckDuckGo. You can read more about it here on the LangChain. This is how you declare tool in the LangChain. So basically, a tool can be just a function, a Python function that takes something and basically returns the output. Here you could specify what that tool is going to do, and you could decorate it. So this is a decorator from the LangChain. If you put this decorator, then it can be treated as a tool. The other way that you could use some tools from the community. So from the LangChain community, that's what we are using this DuckDuckGo search run, so that we don't have to write a logic for it. We can directly use it. So this is how. So we have declared two tools. One is a pre-built community tool. The one is a custom tool, what you see here, and we could bind those tools to the LLM. So this is the list of tools, and we could use the bind tools method and pass those list of tools to the LLM that we had earlier, and then we can invoke that LLM with the passing our let's say the input message. Now let's see what happens. Okay, so you see we didn't get any response from the LLM. So if you go to the Langsmith and see what has happened that we didn't get any response. Let's see. This is what the input that we put to the LLM. But this time, the things that we got, this message we got, AI message, that has something called a tool calls. So it is, so we had already declared to this LLM that we got two tools. One is the calculator, other one is this search tool. And when we pass this input, the model decided to call the calculator with this particular input, and that is why we don't get any answer, rather it represents a call to the function, and we need to handle it. And to do that, you know to do that, and we can also see here in the response that there is a tool call. So if I go to the response, there is something called tool calls, and here are the all the tool calls we see. But there is, since tool call is the list, and there is only one call at the moment, which is this one. And that call, we could see that the name of the function that needs to be called is a calculator, and this is the argument that needs to be passed. This is how you come to know. So whenever you get a response from the model, there is no content, there is no response in the form of string, but we could check for whether there is any tool calls involved, and that's what we're going to see. So we will create some simple mapping that if the model says calculator, I want to call my calculator function, or which is basically a tool, and if it is DuckDuckGo, I want to call this one. And here is the function that we define to handle such a tool. So we will take the response that we got from the model, this is above response, and we will also get the tool mapping, right? Here first we will check whether there is any tool calls or not. If there is no, we will simply return from this function. If there is a tool call, as I told you, the tool call is a list. Basically there could be multiple tool calls. That is the reason we are iterating through the tool call, and for each tool call we are taking the name of that tool that needs to be called, basically that function, and its arguments, and finally we are using that name to get the actual function, and we are just invoking that tool, just like what we saw above. Here is this DuckDuckGo tool, and we are just invoking that thing. We are invoking that tool, and yeah, we are printing the response. So let's declare this one, and we can test it now. So whenever we pass response, we will pass that response through the handle tool calls to see what we get. This is what happened. So these are the two queries. So when we pass, let's say the this expression, the tool executed, which is actually a calculator, and for the other one we asked the recent news, it executed the DuckDuck search. As I told you, since these are the tools are also the LangChain component, we could use the LangChain expression language to invoke them directly. So I could actually invoke them directly also. Okay, just to show, I should have shown that thing. So if I have this tool, and I can invoke this tool directly with the same thing, what let's say I could invoke it directly, and I should get the response from it. Yeah, so we get some response directly from the DuckDuck, that search, DuckDuckGo search. This is what I call the LangChain expression language. Okay, and again, you will be having access to the code, so no need to worry about it. It's simply iterating through the tool call list, getting the name of the function, and simply invoking the way we just invoke down. Nothing big deal here. So we just saw two things now. How do we initialize, invoke the LLM, then how do we attach some tools to the LLM and handle that tool calls. Now next, let's see what we're going to see. Structured output. This is also required to complete our project, or let's say whatever we are building, that we need to have some way to, because if LLM is going to produce some kind of a let's say the plain text output like this, we won't be having control over the parts of this output. Sometimes we want this output to be in a structured format so that we can access its parts in the downstream application, and that is where the structured output is important. So what does that mean? So when we ask an LLM to generate the response, we are telling what kind of response structure we are expecting. Okay, so in this particular example, let's say I want to give a structure called person info, and I'm looking for the name of the person. This is a pydantic model. You could use the pydantic to define that what we are expecting. So this is the name that we want, and here is the description of it, that this is going to be the, let's say, full name of the person, then age, occupation, and skill. So this is the structured info I want to extract. And just like we had this earlier function called bind tools, we have a function called with the structured output, and we can pass our pydantic schema and attach to this LLM. And just like the other, we could now, let's say we are taking this input and we are invoking through the LLM. When we get the result, we will have this data in a structured format. So from this data we got the proper name, age, their occupation, and a couple of skills that was mentioned inside this input. So this is very much useful, right? Imagine this particular text is your resume, then using this you can extract all the let's say all the details of the person in a structured format, and maybe you can then put this in a database and then use natural language to SQL to query the data. So you can simply say that, okay, give me all the candidates with the software engineer occupation, and you can get all of them back using the natural language to SQL. That is also I have covered in the earlier videos. So again, yeah, there is something on natural language to SQL. It's an old video, 1 year back. I might create the new one because syntax keeps changing. Okay, Now we got, now let's look at into the Langsmith also what we got. Okay, so this is what we just asked. This was our LLM, and you see we have given it an output schema, that what output we are expecting. We pass the pydantic schema. This is how it looks here. This is the input that we pass, and with this schema we got the AI response like this. So that's why we are able to get the name, the occupation from the response by using let's say the object notation. We are able to get that details back. Okay, now we have all the prerequisite, I would say, that LLM tools, structured output. Now let's start building a basic LangGraph chatbot. That's what we're going to build. And let me again show you the architecture what we had. We know that the LangGraph is all about basically a graph. So you got a nodes. In our case, we got these 4 nodes, and then there is a connection between those nodes, indicate how the the request or information should flow through those nodes. And this is called edges, and these are the nodes in the graph. And yeah, there is a start of the graph, there is an end to the graph. And since you know that, let's say router is forwarding that request to answer node, or going to the RAG lookup, there is some informations getting exchanged or shared across all these nodes, and that information is called the state. You can define the state as some kind of like a dictionary or object that is getting shared across all those nodes. So if, let's say, RAG put, let's say, retrieve some chunks, it can add those chunks to the state, and that is getting directly available in the side the answer node, because it is also sharing that state. So let's see what all those concepts in a action. Let me go back here, and again we have to install the LangGraph. So here's what we are declaring: the state. So state is nothing but what information I want to share across these nodes, what we just saw here. So currently we are saying that our state is going to be this pydantic model, and basically it will have only one thing called messages, and that messages is the list of those message. This one, like annotate, add message, basically telling that when the states get updated by the nodes, then this message should get appended to the messages array rather than overwriting it. And we will see that as, let's say, this state moves through the system, this basically our message array gets bigger and bigger. That's we will see. Yeah, so we could declare a node here just like a Python function. So we're going to use only one node called the chatbot node, and that node is taking the state and returning the state by processing it. Now if you look at what is exactly happening here, we are simply passing those list of messages through the LLM, and LLM generate the response. We know that LLM only generate response as a single AI message, but still you will see that this message array, when get its return, this will not override the existing messages if we have those messages inside this message array. So let me run this chatbot node. Now here comes the part where we actually assemble the graph. Okay, we require those start, end, and the state graph. So we are declaring a state graph here, where we are passing the state that we have declared above. And then since we got only one node, we will add that node to the graph. So we are calling that node as a chatbot, and then this is the node that we just declare, basically the function name. And then we will say that from the start it should directly go to the chatbot node, and from the chatbot node it should end the conversation. So very simple single node thing. We can compile and we can visualize it so that it's clear. Start means whenever you invoke the graph from start, that is the start, that will directly go to this chatbot node, process the messages, and you will get the response, because there is nothing happening. So here is not much thing with respect to the state. Maybe once we see the complex example, we will see. So let's test this chatbot here. So I created this function called test chatbot, where you can pass your message, and then that message we construct as a state. Let's say the message is with the single message. That's what, because we know that each of our nodes should get the messages array, and that is what we're going to pass through the graph. We will get the result, and we will only care about the last message, even though the state will have both the messages, because the recent message is the response from the the model, and we are getting that AI response. So let's test it. Okay, so I just passed hello, my name is Pradeep, and this is what we got the response, that this one. Then I asked the second message, do you remember me? Then it is saying I don't have access to the previous information. Yes, because there is no memory. When you execute graph two times, so we are we invoke the graph two times, subsequent is two queries, but the graph has no memory to remember across the different queries or different invocation, and that we can verify from the the line graph. So if I come here and look at my first query, okay, if I look at this one, chat model, that I inputted this human message, I got the AI message back. Okay, this was the first message. But what I wanted to tell you, I told you, right, the graph state always, let's say this is the graph state. You could see output is always the what was the first message, and then what was the output has two messages here for the graph. Why? Because the graph state is appending whatever we are saying and whatever the AI is saying. That's what happening, that when we declare the state here, right? So earlier we declared the state that whenever the new message whenever that messages array gets updated, it should get appended and not the override. That is the reason you are seeing this graph state after having these two messages. Now let's go back to the next message, the next query. Here if you go to the LLM and you see there is no previous information, because this is totally an independent run. Now we will see how do we add memory to it. Okay, so let's add the memory. So we are using this LangChain memory saver, and we have to just declare that this is in memory. I think this is just for the demo purpose, but if you want to use the production better, we have to use some more persistent memory that we need to do. When we build solution for our client, mostly I don't use the LangChain own memory, rather I handle memory outside. So I stored all those past messages inside the database like a PostgreSQL, and then basically read based on the session ID or thread ID and pass through the system. So basically memory I kept outside of the LangGraph, but here you could use the LangGraph memory also, and this is how you could use. So when you build a graph, you have to just pass your memory, that saver, so that whenever you run or invoke something, LangGraph will remember what you said, and to remember it requires some ID. Okay, so that ID you can pass as a config. So here we are passing thread ID. So all the messages you pass inside the single thread ID or the common thread ID, they will get remembered. So let me show you how it is. Same, nothing has changed. The graph has remained the same. Only thing is that we added the memory to the graph. Now let's invoke this one with the memory. Now I'm giving thread ID at this thread 1. Both the places I have given as a thread 1, that is the reason it can remember me. Okay, so I ask, my name is Pradeep, and it is able to remember it. Why? Because it has access to my memory, because I'm using this thread. And let's see what's happened inside the Langsmith. This time when I ask, hi, my name is Pradeep, it is just same as the previous, because it is just the first message inside that thread, and that information should be available in the metadata. So yeah, so you could see the thread is called thread 1, and I can go, what is my second message? Second message metadata is also should have, yeah, same thread 1. That is the reason the second message has my previous chat history, my first message and the first reply, and here is the new one. That's what I call it, that I have, once you add the memory, and if you add this config identifier, which is the thread ID, then basically it will have access to your previous messages inside that thread, which is called, let's say you can call it a conversation, or you can call it as a session also. And here is what I said earlier also. Every time this LangGraph you start invoking, this state get all the reply, all the previous messages, because every time message comes into the system via user or via any node in the graph, it's get appended to the system, this state, and state has everything, at the end. Okay, this is good. We are able to remember, we are able to ask the follow-up question. Since you are able to remember, you can ask now the follow-up question, and that's what we did. Now let's see how do we attach the tools. Earlier what we saw, so when you add tools to the LLM, you need to do something called handle tool call, because LLM is not going to call your tools directly. It's just going to tell you, hey look, you need to call this tool. So we need to have some way in the LangGraph also to handle those tool calls. And to do that, let's see where it is. Okay, so we declare a new state. Again, I'm just calling it as an agent state. Tool we already defined earlier, so no need to define them again. So this, it's the same thing, just the variable name is called agent state. We declare again our LLM, and we bind the tools to the LLM here. Same thing, nothing has changed. Only thing is that now we need a special node to handle that tool call. This time we modified our chatbot node also, just to show you that you don't have to just pass whatever you got in the state. You, since it is a simple Python function, you can have any logic here. So here we are taking all the messages till the point from that state, and then we are adding or prepend our own prompt at the start. So this is the we are concatenating two lists. So this is our system message, and this is whatever we are getting it. This is just to show you that you can manipulate this, not just have to stick to the messages. You can have any logic code here, and that's what this chatbot node is doing, and then returning that response. And to handle these tools, there is a special node called tool node. They can represent the tools that you could invoke them whenever LLM wants to call those tools. So let me show you how to do that. Again, just to remember, we got the calculator tool, and there is one other tool called this DuckDuckGo search. So this is what you do. This is simply, you just simply take the tool node, pass the list of tools. Now you got the tool node. So we got two nodes now. You got the chatbot node, and there is a tool node. But as you have seen, basically, that there are some edges. Once you have the two nodes, there are some edges between this thing, right? So we need some logic that when should you go from, let's say, chatbot node to the other node, which is basically tool node. So there should be a way to know, and that is what the condition logic that we have to specify, and that can be specified using a function. So this is a function that we will define on an edge. So here it is saying, what it is saying, whenever let's say this function, where we're going to use it. So let me show you how we're going to use it before I actually show the actual definition. This is how we're going to use it. So we will add these two nodes now called chatbot and tools node. And again, the start node is the chatbot, that we're going to always start from the chatbot. Now here we are saying that from this chatbot, we can go to end node also, and we can actually go to the tools node also, depends on the query. That's why it is now conditional edge. And when and how we're going to decide whether to go there or not, this will be decided by the should continue function. So the syntax means here, when I am at the chatbot node, so basically I already invoke the chatbot node, and then from chatbot node, this function output will decide whether I will go to the tools or whether I will go to the end. Now let's look at that logic, what it decides. So should continue, what it is doing, it is taking the last message from the the state, because as I told you, this will happen once the chatbot nodes get executed, and then it will check does it has a tool calls. It is basically same thing what we wrote here, uh, where it is about I think yeah, sorry, here we are checking the same thing, whether it has tool calls or not, so that it can decide. And that's what happening there. We are checking the last message, and we are checking does it has a tool calls. If it has a tool call, let's go to the tools. If not, let's end it. That's what it is saying. And based on that, the graph logic will happen. Let me run this thing. Okay, tool node is not defined. Where did I declare the tool node? Okay, here. This is how the graph looks like now. From start, it will definitely go to the chatbot. So there are two kinds of edges you see. One is a concrete solid edge here. One is this dotted line edge. So this solid edge indicates that this is going to always happen. From start, you will always go to the chatbot node. But from the chatbot, there are two dotted edges. It means it can pick up any one of them. It can either go to the end and end the conversation by giving the reply, or it can go to the tools. From tools, you can see there is only one solid edge that is going to the chatbot. So whenever it comes to the tools, it will always go back to the chatbot. That's what happening. And to test this, we have this function. This time we will use the streaming, because many times you would wants to have a streaming instead of directly getting all the response at a time. So we could use the stream, which will stream the events one at a time. And it's interesting, we will see now. So there is a a function we declare called chat with agent. As I told you, we will use the thread ID here, so that we could have the follow-up question and the conversation kind of a thing, right? Now we declare our configuration because we need to pass them while invoking here. So whenever we get the messages inside this chat, this message is nothing but the user query. Okay, we are just constructing this a dictionary which has one key called messages, because this is how our state looks like, and then we're going to pass that state inside the graph every time we invoke the graph. Now let's do, and whenever we invoke the graph here, we get an event, and we check whether that we get an event. And for value in the event dot values, so basically event will be a dictionary, and we are checking whether this messages key inside the value that we are getting, because we want that last message. So this is the last message, which is the response we got from because the messages will be big. We saw that every time graph finishes the execution, it keep all those messages inside the state. So we only want the last message. So we are getting the last message, and we are checking whether it has a content field or not. This is just for us. It has nothing to do with the reply we already got. It is just to print here to see whether the response came from the assistant or response came from the tool result. And once I run this thing, you will see what I mean by that. This is just for us to know whether the response came from where. Yeah, so I'm going to ask this one, maybe the first question. Okay, so I directly got response from the assistant. It means there was only one event. So when I executed my query, there was only one event, and I can go and check inside the the LangGraph that it didn't go to the the tools node. So when I say I'm Pradeep, this is only the chatbot node. From chatbot node, I directly got the response because maybe the should continue decided to end it. So this should continue decided to end it because there is no tool required. Now let's say I ask something else. Maybe I say this one, some kind of a mathematical expression. This one. Okay, this is what I mean by here. Here you got only one event when you ask this thing. This time we got two events. So first we got the tool. So basically this loop runs twice. The first we got event from the tool, and then we got event from the the final chatbot node, and we should be able to see that thing inside the, yeah. So when I ask this one, so let's look at what happened. The should continue. Should continue decided that we should go to the tools because it knows that this is actually coming from the chatbot. It's not the should continue. So when chatbot has access to the calculator and direct search, the it decided to call the calculator. And then in should continue, we just check, does this AI message has a tool call? If it has the tool call, then basically we are simply outputting the tool. So the logic of identifying which functions to call is here, and this should continue is only deciding whether there is a tool call or not. And then basically it goes to the calculator tool. We got response from the calculator, and then this response again fed to the chatbot node, and we got the final response here. Again I told you the chatbot node has access to all this information as an input, because the state is getting increase. We are adding more and more messages to the state, and this is what the final answer. And the LangGraph will have all the messages inside its output. Now here you see everything till the point we have executed, and this is how it is behaving the same way the way we have the architecture. So our architecture is that from chatbot it can simply end by giving simple quick answer, or it can decide to use the tools, and from the tool it again has to go back to the chatbot to generate the answer. That's what happening. And yeah, it can pick up the other tool also if I ask something here, but I think you got the point. Now let's stop this and let's go to the final thing that what we have seen at the start. So these all things what we did is to just the build the all the requirements what. And I guess, do I have the same image here? Yeah, this is the same thing. I think we have seen already. This is what now we're going to build. At this point I think you all are already familiar with the graph node agents and everything. And this time we're going to build a RAG agent. So basically you also need to know the RAG, its concepts, and those things. It's hard to cover all of those things in this video, so I have a dedicated video on the LangChain RAG. You can go and check in detail how to build a RAG from the or RAG using the LangChain. Here what I'm going to do, I'm just going to use this code snippet that is sufficient to show me the show the demo to you. And but I will just quickly go through it so that it doesn't feel like alien to you. Basically, yeah, from the LangChain community I am going to use different document loaders. So we have a document loader based on the type of the document I have. So I want to have a support for the PDF loader, the docx loader, and the maybe this is the markdown loader. And then from the LangChain community, yeah, it can read directly everything from the directory. I'm going to use embedding from the OpenAI. The vector store, I'm going to use Chroma DB. And what else? Yeah, so these documents we want to split it right into the small chunks, and we will be using this particular recursive character text splitter. Okay, now let's we need to install this all this library which supports the the loaders that we saw. A simple function I have declared. We just take the folder path. I already put some dummy documents which I hypothetically generated using let's say ChatGPT. They're not the real companies. And these docs which I also use in the earlier videos. I don't want to create the new docs. And here we are basically there is already one Chroma DB, so this might give an error because I had run this notebook. So let's see what happens. So here we are loaded those 5 documents. This is simply iterate through each file in the path and just check whether it is PDF, docx, or any other file. So currently I have only PDF and docx, and I got those 5 documents loaded inside these documents. Now I can split the, so if you want to see what is documents here, let me show you. If I take the 0, the first document, this will be a document object from the LangChain. So this is a document object. It has some metadata, basically name of the file, and it has this is actual page content that document has. Now we want to split it. Currently my documents are already small, but if you will be having usually bigger documents, you need some splitter. So I'm saying that make each chunk size to be 1000 and have some overlapping between those two chunks, because sometimes it gets cut into the middle. So I just want to make sure at least one of those chunk has a complete sentences. So having 200 character overlap means if it, let's say, cuts here, then again in the next it will start from somewhere here, let's say 200 characters for the next chunk. And let's set up our vector database. We declare the OpenAI embedding model. I'm using the embedding 3 small model. I am using this method from the Chroma called from documents, where I could specify my documents, which is basically the chunks that we got here. We can check how many chunks we have. So we got 8 chunks. So there are actually 5 documents. So some of those documents are more than 1000 characters. That is why we got, let's say, the more chunks. And here we could build our let's say the vector database. Okay, we got our the Chroma DB vector database. This might have created a duplicate record, so better I give some different name here. Let's say I call the Chroma DB 1 or something, just to make sure it didn't create a duplicate thing. And then if I run it, I should see a one more folder coming. Yeah, Chroma DB 1. So this is what, let's say, we got our the Chroma DB built with those 8 chunks. And using LangChain, we can take our vector DB and then basically create a retriever. So basically directly you can invoke, again, this LangChain expression language, you could invoke any component. So I'm just, to make sure that our vector DB is set up properly and it is working, I'm going to ask, when was this Green Grow Innovations was founded, and I know it was something related to 2010, and we have that document. So this is working. We got the, and we are retrieving 2 documents here. So the at least vector database is working. That's what we saw. Now next thing is this time I will use the Taveli search. So earlier I used DuckDuckGo, but let's try this time I'm using the Taveli search. You have to go to their website and basically get the key. And I'm going to define the same way the way earlier I defined. So I'm defining this web search tool, which will take the query. I will invoke the this Taveli search, and actually it get a lot of items. So let me show you what we get. Yeah, so it gives us these are the parameters that we can pass, but yeah, we get so much thing inside the result that uh, we can ask to include. Yeah, I just want to show you the output, what we get in the output. Do we have here, or we can see that output, we can invoke and we can see what we get inside the output. So basically this is the web search tool, right? So we can execute and see what we get inside the output. Yeah, so we are formatting this based on, but I want to show the raw thing we get. So I can use this Taveli directly and invoke the query. Yeah, let me do here to just show you what raw thing we are getting from them. Yeah, this is what you get for the query response. You got the query that you ask, and there is no direct answer. Yeah, you could even ask for the direct answer, I guess. Yeah, include answer or not. Then what we got, then we got the results. So results are actually a list of things, and each list or each object in that list has some URL from where we got. I think it's scrap LinkedIn, then the title, the actual content that it got. And I think, yeah, there could be maybe this one it got from the YouTube. Yeah, so yeah, it has some diverse sources, YouTube and something. But what we want, I just keep it simple. So I just included, I want to include URL, I want to include title and content. That's what I did here. So whenever we get results, I just want to include the title, content and URL and nothing else. And that is what I want to concatenate and give it to the our agent. Okay, that's what this tool logic is here for the web search. And for the RAG, we have already seen here. So we can invoke the RAG, right? So I'm also integrating that thing as a tool here, a RAG tool. And inside that, whenever we get the query, we invoke our retriever, and we know that we get something like this, a document object. So but document object has a field called page content, so we want content from there. And that's what we do here. So whenever we get those docs, we will iterate through them, we get their page content and concatenate with this, let's say, 2 new line character, right? And we can see what we get. To just make sure that we get the plain text and not this document object. This is what we got, the plain text. Again, all these things we have seen earlier in the previous video. You can go and watch my RAG video to get the idea. Okay, enough. Now we have declared our tools. Let's declare the setup identity schema, because we need some structured output, as I shown you, right? Every time it needs to take a decision whether to go where, so we will use the structured output for that decision. So we got the route decision, and we are expecting that it can give us the route, basically the next tool name where to forward the request, rag, answer or end. And it could also an optional reply. We saw that it can give the I think it's not optional, it can give the reply or it can give me the none basically. And then there is one more we require, where we have this judgment. So in the rag we have to decide whether it's sufficient or not. So this identic schema is actually used inside that LLM, and here we are specifying those LLM. So we got some called the router LLM, and that router LLM with the structure output we are putting this root decision structure. For the judge we are putting the this one, a structure output. And for this one we don't require anything because we are giving the plain text output, but this is intermediate steps we do require. And now this time we define our agent state like this. We say that okay, messages is going to be anyway we require, but then we also want to store the what is the current route here. And then this is the current route. And then yeah, what we got from the rag and what we got from the web, this is what we got. We have to decide. Here I'm not using that annotated thing. Let's see whether, even I haven't noticed this thing earlier, I'm not using this annotated, whether the graph state get added or not, we will see those things. And because we do have the memory that goes through different nodes, let's declare this agent state. Now let's work on the router node. We know that the router node, we already attached a structured output to get the next node. So we are saying that you have to make a decision. If it is something like a small talk, a greeting kind of a thing, you can directly select the end node and you can reply yourself. If it requires some kind of a lookup, then better you pass on to the rag node. And if you think that this can be answered without any external information, pass on to the answer node. So this is where we got this prompt. And since we have this prompt passing through the LLM is going to give us the the result. Basically we know that it will have a root, and we are returning that information. So we are returning the messages that we got. This is the state of messages, and then we are passing our state back. So even though it is going to overwrite, we know that we are passing the whole state that we got inside the messages and the decision of the what we got. And if it decided to end the conversation, then basically we have the state and then its own reply, whatever it's going to reply, that will become the last message. So here there is no last message, but in this case there will be a message from this particular router node, and that's what we have declared. Let me zoom in. Okay, now here is the web node, basically web search node that we are defining. Sorry, no, sorry, I just shown you the router node. Now we should look at the rag node. The rag node will simply call our rag search tool that we have declared above. It will call the rag search tool, get the chunks, and we also have here one LLM call. We already know that it has to take a decision whether the retrieved chunks are sufficient or not. That is taken by this particular, what I say, that is taken care by this particular LLM prompt, and it will tell us whether it is a sufficient or not. And based on that, it will return the state what it has, and it will attach its rag chunks, because we know that our agent state has also filled for the, did we declare above or below? Where is the agent state? Okay, here we have filled for the rag, we have filled for the web, and that's what the rag node gonna do. It's gonna return the rag chunks, and it's gonna also return its root decision, which is based on this verdict, whether it has to go to the web or it has to go to the answer node based on the chunks are sufficient or not. And finally web node, webs we are calling the web search tool, and from the web node we know that we have to go to the answer node. So that logic from the web node, you can see that the solid line, not this one actually. When we print the graph, you will see we are going to the web node, we are going directly to the answer node, and that's what it is doing. So we execute the web search node and return the web attribute, and then basically the next route what we want to return. If you observe one thing here, I'm not using the tool node, because this time I decided to, instead of using tool node, use our normal nodes, and then inside the normal nodes we can call any tool, because we have full flexibility to what to do. That is what I wanted to show you. The rather than using that tool node what the LangChain is giving, you can have a simple node, let's say called web search, and then inside the web search you can use that tool. You don't have to use the tool node that what the LangChain is specifying. So these are the nodes we got, and then the final answer node. Whenever this state, it receives the state, it will check, do we have anything from the rag, do we have anything from the web, and basically it create the big context. Okay, and we have the simple rag prompt that says, based on this context, answer this particular the query, and that is the simplest one that what we got. Did I run them? Hopefully already ran them. Now there comes to the routing. Since now the decision logic is easy, because inside the node itself we are getting the value called root. Each node is deciding themselves where to go, right? So inside the node here, in the router node, it has already given us the field called root, where to go the next. Then the RAG node also is returning the root. So in the ages logic, we simply have from routers, whenever we will receive the agent state, we will check, we will simply return the whatever the state set by that particular router. Here we will return the state set by the the RAG agent. So we are simply returning the whatever we got, and this is how it will look. So we are adding all those nodes in the graph, and basically we are adding the conditional edge from the router, that we can go to the RAG, or we can go to the answer node, or we can go to the end based on this logic. So whenever we get the output from the router, it will set that root field, and based on that root field it will directly decide where to go, because root is going to be one of them. So it is simply one to one mapping, nothing. So there is no logic inside this. We are not manipulating here state, rather we are just using whatever we got from the the node that we came from, and it applicable to the same thing. So let me visualize this graph here. Before that, let's visualize this graph, so that yeah, we could see here that from the start we always go to the router node. From router there are three dotted edges, that it can go to the RAG, it can go to the answer generation, or it can directly answer itself by going to the end node. And from the RAG you can either go to direct answer if it is sufficient, or else it can you can go to the web search to get the more data, and then from web search you come here. Why do we have a conditional edge? Actually from web search we should directly come here. So where is our web search? From web search we don't need to add any conditional edge, which is, see, we are just coming here. So from the web search we don't need to add any conditional edge. From web search we are anyway going to, let's say, the from web search we are directly going to the answer node. This we don't even require, I guess. Yeah, we have to just come here, nothing else. Okay, what happened? It's taking time. So yeah, from web search we should directly come to here. There is no other thing we are doing. Now let's quickly see this demo. The video has got longer, so let's run this what we just just saw, and it should do the similar way what we have seen earlier. So I say hello, and it has given me the quick response. Hopefully that is directly coming from the I think this demo we have already done at the start, so we don't need to maybe even though when it's already thing. So yeah, so router node directly answered, and then I say directly okay, let's take that one, that what was not getting correctly, right? We can check again that the vein was green grow found it. This was not coming, right, because of the prompt. So we need to optimize the prompt to make sure that it checks the RAG. Yeah, I think it has checked the RAG. That's why we got this one. Okay, so you have seen this, how it works at the start itself, so I don't need to repeat that same thing here. We go from router to the RAG, and then finally the answer generation. So we have seen this demo at the start itself, no need to repeat. As I told you, you will have access to this Colab notebook, and let me know whether you are interested that I should create the second part of it, where actually I integrate whole this thing inside the FastAPI, and also we create a endpoints for the vector database, basically adding the files, deleting the file, proper a production ready kind of a setup. I think already those stuff inside this LangChain track course, you can watch there also. But yeah, if you're interested, let me know. I can create the fresh new video just as a second part for the LangGraph FastAPI integration. Hopefully you find this video useful. You can explore more about our what we build inside our case studies. We also got a blog where you could read more about what we do. Recently haven't published anything, but we will be publishing soon. And then you can also check our platform, which is currently still in the under development, but you can build the similar RAG agent or AI agents on the future smart agent. So you can go to the agent.futuresmart.ai, and basically you can try yourself and give us the feedback. Thank you.